All right, good morning. We start chapter 16 today. Up until now, we've been learning about electric field and about some of the kinds of patterns of electric field that we can create with different charge distributions. And basically what that's allowed us to do is reason about forces, because electric field is basically the force per coulomb, or since a coulomb is a unit of charge, we say the force per unit charge that would be exerted on a charge if it happened to be somewhere, so that we can reason from, if we can calculate field, we can calculate the force on something, and then we can predict its motion. So basically we've been reasoning about forces. However, there's, as you know from last semester, there's another way of reasoning about physical situations, which is reasoning about energy. So when we talk about energy, if we have a system with more than one object in it, it can have kinetic energy and potential energy. And so often, for some system, we would have, depending on how we defined the system, if we took everything of interest to be the system, then conservation of energy told us that the change in kinetic energy plus the change in potential energy of the system had to be 0. And we need to be able to reason about electric phenomena that way too. So just as field is force per unit charge, we're going to find that we can say electric potential energy is equal to, so force is Q times E. We want the electric potential energy change in some process that involves a charge moving in a region where there's things interacting with it and there's a field. We want that to be equal to the charge times something. And what that something is called, and what it's going to turn out to be, is called delta V, the change in electric potential. So we'll find the potential, or a change in potential, similarly to this situation, is the change in potential energy per unit charge from some initial state to some final state. Because when we talk about energy, we're always talking about two different states and what happened in between them. Doesn't give us information about the detailed motion of things, but it does put a lot of constraints on what's possible to happen. So that's what we're going to be talking about for the next couple of lectures. And so we're going to be talking about, we're exploring this concept of electric potential and getting used to working with it. Now, a really quick review of potential energy. Remember from last semester that we talked about it, that we have to be very careful about our choice of system. So if we choose a system that's a single particle, there's no interactions within the system, and so there is no potential energy. What happens is that the the energy of a single particle a single particle has kinetic energy and rest energy, and so the change in energy of a single particle, the change of its kinetic energy was equal to assuming mc squared, the rest energy doesn't change, the change in kinetic energy of a particle is just equal to the work done on it by external forces. And most of the situations we're going to be considering here, we're not changing rest energy, we're not considering particles turning into other particles or whatnot. And at low speeds, remember that kinetic energy was approximately equal to a half mv squared, where m is the mass of the particle and v is the speed, right? So this should be amazingly familiar. Now, remember that also that delta means the difference, so delta K is the kinetic energy of the final state minus the kinetic energy of the initial state. And remember that this is work done by, let's write work done by the surroundings here, not external work, which is the same thing, but work done by the surroundings. Remember that work is the product of a force exerted over a distance, right? And so remember that work was the x component of the force exerted by the surroundings times the x component of our system's displacement plus the y component of the force exerted by the surroundings times the y component of our system's displacement plus fz delta z. And then we can write this as F times the dot product of two vectors, the force and the displacement. And so inherent in here is the dot product, because what this means is fx delta x plus fy delta y. And it's, even though we're starting with vectors, the end result is a scalar, right? So for example, if we have a ball going up 1 meter, then, and the ball is our system, and it's near the surface of the Earth, then the change is just equal to the work done on it by the Earth. And work, well, we have a force mg downward, right? So let's say the ball's mass is, it's a heavy ball, its mass is 2 kilograms. So the work done by the Earth, we have to be careful. Is the work done positive or negative? Negative, right? Yeah. So we have, so fx delta x, there aren't any x components in this process. So we have fy delta y, which is a minus mg let's call that H, just to be symbolic here. H. And so the change in the ball's kinetic energy is negative. It slows down. That makes sense if it's going up near okay. And there's no potential energy involved because we chose the Earth is our system. I mean, the ball is our system, so one system, right? Okay, this is all okay. So if we have a system that has more than one object in it, though, and they're exerting forces on each other, and this is a situation that we're going to be in all the time in semester because there are always lots of charged particles around, right? Then the system is many objects, and they're interacting. So if we have charged particles, we could have a positive charge and a negative charge and another negative charge, and they can be exerting forces on each other. So there's a force, and those two repel each other, and those two attract each other. So there are lots of internal forces, forces internal to our system. Then the change in energy of this system is due to two things. Or the change in kinetic energy of the particles anyway. It's due to work done by things internal to the system and work done by the surroundings. And so what we do is to make everything related to our system be together, we say that, so this is internal to the system. So the sum of the change of kinetic energy of the system and the negative of the internal work, the work done by internal forces, is equal to the work done by the surroundings. And we called this thing the minus internal work was the change in potential energy of the system, right? And so now we're back to delta K plus, so the change of potential and kinetic energy of the system, the change of potential energy of the system, equal to work done by the surroundings. And if we're inclusive enough in our system, then there's going to be nothing significant in the surroundings, and so that'll be negligible. And in many of these cases, we're going to be choosing our system to include all interacting charged objects. And the other thing that's going to be true in most of the analyses we do is that even though most of this stuff is occurring near the surface of the Earth, electric force is so big that the effect of gravitational forces is really going to be almost negligible. It's very small. So we'll often be neglecting the effects of gravitational forces and just looking at the effects of electric forces when we do our analyses. Okay, so let's look at a system of charged objects. So we have a proton entering a capacitor through a tiny hole. And this side is charged positive, that side is charged negative. The capacitor, when we draw squiggly lines like this for a capacitor plate, what that's intended symbolically to mean is that we only drew a little piece of it, but it's really big plate, so it like goes down into the basement and up into the second floor. So the gap is very much smaller than, gap distance is very much smaller than the radius of the plates. So think about what you know about the electric field inside a capacitor. So here's our proton. What happens to the proton? If we choose the proton and the capacitor and all the charges on the capacitor and the electric field inside the capacitor as our system. Okay, so what happens here? What happens to the kinetic energy of the proton? Okay, so let's have some votes here. Fingers. Wow, really? Okay, so we got 3s and we got 1s, and did I see anything else? Okay. Well, let's think about the inside of the capacitor here. So here's these positive charges, and here's these negative charges, and here's our proton heading this way. How would I draw the electric field in this region? Yeah, okay, so positive charges here, negative charges here, so we have an electric field in here. Does the proton feel a force due to this electric field?
Yes.
Yes, 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 yes. And what direction is that force? Same direction as the field. So we have a big force here, don't we? So you want to rethink answer 1?
System is everything, right?
System is everything, but is the kinetic energy of the, so what's happening to the proton? What's happening to its speed? It's increasing, isn't it? What's happening to the speed of the capacitor?
It's faster. Oh, it stays the same.
Nothing, right? It's not changing. Okay? So what happens to the kinetic energy of the system?
They go increase.
Yeah, so delta K is greater than 0, and therefore what must be true about the electric potential energy of this? Yeah, it's got to go down, doesn't it? So delta U is less than 0, and so that looks like answer 3. So if you said 3, your reasoning was correct. So questions about this? Okay, so how would we calculate the change in electric potential energy here for this process? So the change in electric potential energy, so we know how to calculate the change in kinetic energy. If we know the initial speed and the final speed, we can subtract a half mv final squared from, we can take half mv final squared, subtract a half mv initial squared, and that's a change in kinetic energy. So how do we calculate the change in electric potential energy? Well, since it's minus the work done by internal forces, and this force here is a force internal to the system because the system includes the capacitor and all the charges on the capacitor. So the things making this force are part of the system. So we're going to say it's minus fx delta x, and nothing in y and nothing in z. And we know how to calculate fx. That's just ex delta x. And there's a q here. And actually, in this case, we know it's a proton, right? So we'll actually write a minus plus E times EX delta X. And so that's the change in our electric potential energy, right? So if EX is 300 newtons per coulomb and delta X is 2 millimeters, then this would be a minus 1.6 times 10 to the minus 19 coulombs times 300 newtons per coulomb times 2 times 10 to the minus 3 meters would give us our change in electric potential energy, right? Now we have to be very careful about signs here. These are not magnitudes, these are components. So that's the thing that you write inside the vector. And so we have to note that the component of the x component of E is positive in this case. And the displacement x gets bigger. So delta x is a positive number. Okay, we have to really pay attention to signs to get this right. Okay. Same capacitor, except now this is an electron, and it's moving. It enters the capacitor through a hole, moving in the same direction to the right. Now what happens in this case of the system? System is still everything. Okay, so what's happening? Okay, 2 is correct, right? So in this case, the electric field's still in the same direction. The velocity is still in the same direction, but this is now an electron. So the force is in the negative x direction. And so the electron is going to be slowing down, isn't it? So delta K is less than 0, which must mean delta U electric is greater than 0. And to calculate, in this case, we want minus the internal work, so that's minus Fx delta x, and that's to in this case we have a minus, E, we have a plus 300 newtons per coulomb, we have the same displacement. What did we say it was? 2 millimeters. And so we have these two negative signs in our product here. So the result is going to be a positive number, and that agrees with what we've got. So in the one case, for a proton, we have the change in electric potential energy is negative plus E times E sub x times delta x. For an electron, the change in electric potential energy was minus E, Ex, delta x. So the thing that's the same in both these cases, just like the electric field is the same in both these cases, but the force changes direction depending on whether the sign of the particle is positive or negative. Well, the thing that's the same in here and doesn't change with the sign of the particle, let's rewrite this. This is equal to a minus E times a minus EX delta X. This is equal to a plus E times a minus EX delta X. The thing that doesn't change is this minus EX delta X. And so that's what we call the change in electric potential. So we can write this as more generally, we get the change in electric potential change in electric potential energy is going to be equal to Q, which is a sign number, what we call delta V. This is change in electric potential. And we seem to have a definition of delta V, which is a minus E sub x delta x, but we just happen to have a one-dimensional situation. So what would happen if it was in the y direction? We get the same thing in the y direction. So the change in electric potential is the negative of the dot product of the vector E times delta x, delta y, delta z. And because there are so many R's in our lives when we're talking about electric fields, we tend not to use R for this. What we tend to use is the displacement called delta small l, and that's delta x, delta y, delta z, and so this is going to be the dot product, negative dot product of, so that's change in electric potential. And it's useful because it just depends of the system that's not the moving object. So it just depends on the field, basically, and on the path that an object is going to take when it moves through that field. Now let's think about units. We have newtons per coulomb times meters. So it must be Newton meters per coulomb. That's clearly a joule per coulomb. So it's energy per unit charge. And that has a name. It's called a volt. So 1 volt is 1 joule per coulomb. All right. So let's see if we can just practice a little bit here and get some. So let's just calculate some changes in electric potential to practice. So this is another of these kind of hypothetical things, just like electric field is, you know, the force that a 1 coulomb charge would feel if it happened to be there. This is related to the change in potential energy you'd get if a particle moved along the path we specify. So the first question is, what is the change in electric potential along a path from B to C? So what's the answer? Okay, I see 5s and I see 6s. So we agree on the absolute value, but we disagree on the sign. So let's check out the sign. So we have change in electric potential is minus E dot delta L. So that's a minus 0, negative 300, 0 newtons per coulomb, volts. An alternative unit for electric field must be volts per meter. Okay, so you'll see it written both ways. Okay, newtons per coulomb. And what is the vector delta L? 0. So is it 2 or negative 2? Negative 2. 0 meters. So we get a minus 0 times 0 plus minus 300 times a minus 2 plus 0 times 0. And that gives us a minus 600, so that's negative 600 volts. Okay, so that's what I meant by being super careful about signs. And being careful about the sign has two aspects to it. One is you have to be careful about the sign of the component of electric field. But the other is you really have to be careful about the path. So final minus initial, so it's 200 minus 220, so indeed it's 0, negative 20. If you actually write this out as vectors carefully, you will get signs right. But, okay, questions about that? Okay. Okay, now the electric field is plus 400 newtons per coulomb in the y direction. B is 0, 0, 0. C is negative 200. What's the change in electric potential along a path that starts at B and goes to C? What's your answer? Okay, I'm saying 5. 5 is mostly 5. 5 is correct because here we have, so it's a minus E sub y delta y. So we have a minus plus 400 newtons per coulomb times delta y. Now y starts at 0 and goes to minus 2, so delta y is going to be a minus 2 meters. And that gives us, we have two negative signs, so that gives us a plus 800 volts. Yes?
Why is delta y not positive 2? If the final is negative 2 and the initial is 0, will it be?
Okay, so how do we calculate delta y? So delta L is the final minus initial, so it's 0, -2, 0, minus 0, 0, 0, and so we get 0, right?
Yeah, I can't draw arrows, so you're doing just fine.
So there's a lot of being careful about taking all the steps. Okay. All right. Okay, so what do we got here? 4. Okay, you're on it. Yes, that's correct. So we have a negative minus 200 minus 300 0 newtons per coulomb dotted into same displacement, -2, 0, 0, minus 0, 0, 0, so 0, -2, 0 meters, which gives us a minus -0 plus -300 times -2 plus 0 times 0, which gives us, that comes out to 0. Now there is an x component to the field, but the displacement didn't have an x component, right? So therefore that didn't matter. The y component times that gave us a plus 600, but there's this minus sign here, so. Okay? Sounds like you got it. Going back to this situation, suppose we had a path that started at A and went to B. So instead of the path from C to B, suppose we have a path that starts at A and goes to B. Never mind those answers. They're not going to be what you get. But what would the answer be? So we're going this, our path goes this way, the field in this region is pointing up.
Would it be 0?
Wouldn't it be 0? It would be 0, wouldn't it? Because the displacement is perpendicular to the field. So the displacement has only an x component, the field has only a y component. This dot product is going to come out to 0, and in fact, the potential difference will be 0. So we actually can generalize something that makes your lives a little easier from these examples. We saw that when the direction of displacement along your path, and this is why it's so important to get the beginning and ending of the path right, the direction of displacement is in the opposite direction from the field. The potential difference ended up being positive. Yes?
So, like, how does this change if the electric field is like curved over the distance traveled, like from the dipole?
Okay, so so I wouldn't say it's curved, but it changes in direction. So hold that. That's a really good question. Hold that question for a second, and we'll get back to it. Let's finish this generalization. if the displacement is in the same direction, then we got a negative potential difference. And if delta L is perpendicular to E, the potential difference was 0. And this is worth noting and internalizing because it gives you a way to check the sign of your answer when you do a long calculation and then you say on physics grounds, what should I get? And the sign of the potential difference is actually probably the most important part of the potential differences you calculate, because the sign determines what's going to happen to a proton when it traverses that path, what would happen to an electron when it traverses the path, is it going to gain or lose energy? So that's probably the most important piece. Now Tristan asked an interesting question, which is, we know that the electric field due to a dipole isn't uniform, right? So up to now we've been talking about uniform field because that was the easy thing to talk about. But the electric field due to a dipole isn't uniform, and in fact we have something like that. And so if we took a path along a direction where the electric field, and in fact it's not uniform in more than one way because it decreases with distance, right? So it's massively non-uniform. So our path could even, if we wanted to, and our path doesn't even have to be a straight line, so our path could actually okay, so here's where we start here. We end up here. What would be the potential difference along that path? Well, the only solution is to divide the path into lots of little pieces. And yeah, so we take a little step here because we know the field here, and so at every little step we'd be calculating, so we'd have lots of little delta L's and lots of E's, and we'd have to, now occasionally calculus helps us out in some nice simple situations and we can do it with an integral. That's not always true, in which case we're back to doing it numerically this way. We've had kind of a lot of experience adding up little pieces of things recently. Which is what we're doing in lab this week, is adding up little contributions of field and then getting in that field and watching a particle move. So that's where we're going to go next time. But for right now, what we're trying to do is to internalize the basic ideas before we get more sophisticated about adding stuff up. Okay. So if we have our definition now of electric potential, which is, or in one dimension, or delta y or something, we can obviously do some algebra here and rearrange this so we get delta v over delta x is minus e sub x, Move the minus sign to that side. And basically that's, if we just take delta x small, right, it turns into a derivative. So we get a minus and so this, the way we say this, so the x component of the electric field is the x derivative of potential, okay? So we can say that the electric field is the gradient of potential. And so, of course, E sub y, the negative gradient of the potential would be minus delta V over delta Y. And that has so what is a gradient? A gradient, I don't know if you've heard that word, but a gradient is just a three-dimensional spatial derivative. So it's, you have to compute the derivative with respect to x, the derivative with respect to y, the derivative with respect to z. So we could write E equals minus dv dx okay, so that looks a lot hairier than it really is. So we can use it in simple ways to solve simpler problems. So let's see this one. Okay. So we can apply this to just do a backwards problem, basically. So it says if we know a potential difference along a path in a region where we know the electric field is uniform, what's the electric field? So before we said we know the electric field, we know the path, what's the potential difference? Now we're just saying we know the path and the potential difference, what's the electric field? So it's just a backwards problem from what we just did, right? And now it's asking for a magnitude. Because we already know the direction. And notice the direction of the path. Okay, the path is from C to B, so it's going the same direction as E, right? So, so what's the answer? Yes, 250 volts per meter. Okay. Now I want to make kind of a point about notation and path directions. This is something that it's easy to get wrong if you don't pay attention, and that inevitably gives you the wrong sign of something. So we have potential. Now for a potential difference you need two things. You need an electric field and you need a path. You need an initial and final location here. So if we say we're taking a path from C to B, we would write this V sub C minus V sub B. So it's final minus initial, right? Now this indicates that there really is such a thing as the value of the potential at a particular point, and that's true. and we will get to that. But right now what we're looking at, we've only been looking at differences because a potential difference allows us to calculate a potential energy difference. And sometimes we write this as delta V C with a little arrow to B. Why that order? Because if you forget the arrow and you write delta V C minus B, that's actually correct. Okay, so start it. This is initial, that's final. So in this problem, let's see, in this problem, they're all the same. Okay, well, never mind. If we had a path from A to B, how would we use this notation? Okay, so we'd have delta V. So it's from A to B, so it's like that. And so it's, what do I write here? B here, A there. Okay. So that's something, there are a lot of details that you have to pay attention to here. So you have to pay attention to signs carefully. And this gives you a way of physically checking your sign. So that's useful. You have to, signs of displacement, signs of field components, direction of the path, particularly important. Okay. All right, well, the next thing to talk about is indeed potential differences when the field is not uniform over the whole path, when it's changing. And we have only about 2 minutes to do that before we have a quiz, so maybe we should just have a quiz, huh?